We're happy to have Professor Tony Gherghetta from University of Minnesota telling us about new 5D perspectives on the QCD.
Okay. Thank you very much. Thank you for the invitation to give this seminar. It's really great to be here in Seoul. And today I want to tell you about some recent work over the last few years on new 5D perspectives on the QCD Axion. So let me just just mention the strong CP problem here. Obviously for this audience, I don't have to go into too much detail, but the strong CP problem is the introduction of the CP odd term in the standard model. And this theta term, this is the theta from QCD, but it also gets a contribution from the quark masses. And so this theta bar is the basis independent CP violating observable. And it has an effect on the neutron electric dipole moment. It generates a neutron electric dipole moment. And from the measurement of the neutron electric dipole moment, we get a bound on theta bar, which has to be 10 to the minus 10. Now, the question is, why is theta bar so small? Now, you could imagine that theta bar is anthropic, but it turns out that it doesn't appear to be anthropic. And our universe, we could still get to our universe if theta bar were as large as 1. And these authors actually put a bound of about 0.1 if you want to get Big Bang nucleosynthesis to work and nuclear reaction rates to work. They found that there was no problem getting to where we are today. So the fact that this theta bar is not anthropic suggests that there should be a dynamical solution, and that the most popular one is the PQ mechanism and the axion. So here is the axion, which is the angular component of this complex scalar field. The Lagrangian here, axion Lagrangian, has this anomalous coupling to GG tilde. There's also a photon coupling and also a coupling to the current. The axion mass is determined from the topological susceptibility, which is this 2-point function of this topological term, GG tilde, and that is what generates the axion mass. And from this, we get an estimate of the axion mass in terms of the decay constant, which is roughly lambda QCD to the 4th divided by 8. Or there's a more precise formula. So that's how the axion mass is generated. And another feature of the axion solution is the so-called axion quality. And that's related to the fact that even though QCD generates a mass and explicitly breaks the Peccei-Quinn symmetry, we know that quantum gravity can also violate global symmetries like this Peccei-Quinn U1. And so you can add to the Lagrangian, to this Lagrangian, you can add higher dimension terms which explicitly break the Peccei-Quinn symmetry. And what happens if you do that, you'll get another contribution to the axion potential, which then destabilizes the axion potential minimum, and you'll reintroduce the strong CP problem. In other words, you won't cancel off the phase theta bar. And so this is referred to as the axion quality problem. And it turns out that to ameliorate this problem, you've got to suppress, these terms have to be suppressed to order 10. This n here has to be greater than or equal to 10. So it's a bit artificial that you have to require this. In other words, the Peccei-Quinn symmetry has to be a very good symmetry, but only explicitly broken by QCD. And other sources have to be completely suppressed. Now, of course, I've assumed here that this coefficient is of order 1. There are arguments from string theory that maybe these coefficients could be exponentially suppressed because they're coming from non-perturbative effects in gravity. But I'm not going to assume this. For the argument of this talk, I'm just going to take this coefficient here to be order 1, and then the question is, why is n here much, much bigger than 10? That's going to be my assumption. Of course, we also, we'd like to know where this dimension 5 axion coupling comes from. But again, the axion solution has been around for a long time. We have solutions. One of them is the KSVZ. where you just integrate out some heavy fermions, which are charged under the Peccei-Quinn, and generates for you this anomalous term. And there's also the DFSZ model, which now charges the standard model fermions under the Peccei-Quinn and has two Higgs doublets. So those are the two kind of UV completions for this dimension 5 axion coupling. And I'm being very quick here because obviously I assume that people are familiar with this. And then finally, just in this intro part, the QCD Axion limits. These are the current limits. The FA here, the decay constant, is constrained to be between 10 to the 9 up to 10 to the 12. Although this limit here, it can be much higher. This comes from requiring the axion to be a dark matter candidate and generating the axion dark matter density from the misalignment mechanism. So if you allow for a more fine-tuned misalignment angle, you can increase this upper bound. But this is roughly what people are talking about when they're referring to the axion decay constant. So of course it's weakly coupled because the decay constant is very big. And therefore, once you know where FA is constrained, then you can get a prediction for the axion mass. It's between 10 to the minus 5 eV and 10 to the minus 3 eV. So that's kind of a lightning review of, I'm sure that people are pretty familiar with this. So then the questions that I want to address in this talk and give a perspective from 5D is the following. Can we further understand where the PQ breaking potential comes from and where the spontaneous breaking scale comes from? The other question is how to solve the axion quality problem, because if you're really looking at a solution to strong CP, you should address this quality problem. And then finally, another question that I want to answer, will give you an answer in this talk, is can the QCD axion mass be different? And so what I mean here is the following. Here's a typical plot that you see quite often. This is the axion mass as a function of the scale 1 over FA. And there are some factors here related to alpha. This is, say, the axion photon coupling, but it's basically 1 over FA. And you see here's the QCD line. So if you're on this band, you solve the strong CP problem. And that prediction is pretty robust from QCD. You don't really have much freedom there to change that mass. So the question I'm going to ask is, could you move the mass, can the axion mass be different but still solve the strong CP problem? That's going to be the question that I'm going to get to at the end of my talk. So these are the questions that I'm going to address, and I'm going to use the fifth dimension to address these questions. Now, why do I use the fifth dimension? Obviously, I've worked a lot in the fifth dimension, so that's an obvious question. But these are the reasons that I think are helpful. One of the things is that it provides a complete framework, as we'll see as we go along. So I'm not just trying to solve one problem and then be done with it. I kind of want the complete picture, and this fifth dimension framework, ADS framework, whatever you want to call it, provides that for me. First of all, we know that if you're in a slice of ADS, that you can generate a hierarchy of scales. And this is good because we know that the decay constant is 10 to the 10. It's much smaller than the Planck scale. So yes, okay, you'll be able to explain that hierarchy. But the other interesting reason to study this 5D ADS is because it gives you a dual interpretation in terms of 4D strong dynamics. So any solution that you engineer in the slice of ADS will have an interpretation as 4D strong dynamics. And so that's one of the main reasons for studying these kind of questions from the perspective of the warp dimension, the fifth dimension. And indeed here, I've shown you a bit of the dictionary, the 5D ADS, where this is the fifth dimension. The fifth dimension is dual to the 4D energy scale. The UV scale is the UV brane is some UV energy scale. And then as you move into the fifth dimension, you kind of run down in energy to the infrared scale. So you've got this nice dictionary. And then finally, it's also, you can use the geometry to generate small couplings. So these are all the attractive features of using this framework to try to tackle some of the questions that I was addressing on the previous slide. So let me begin then with the axion quality problem. So we're going to be working in a slice of ADS. So here's the metric. Z is going to be the fifth coordinate. And this warp factor out the front, this A factor, it's 1 over Z, but there's going to be a scale there. That scale there is the ADS curvature scale, K. And then I want to, if I'm going to explain the axion quality problem, I have to put in the source of explicit violation due to gravity. Well, that I can do because I've got a UV brane, and on that UV brane, that's the scale of where gravity, that's the Planck scale, and there is where I'm going to localize all violations of the Peccei-Quinn symmetry. And then in the bulk, I'm going to put the axion in the bulk, and I'm going to put my Peccei-Quinn symmetry in the bulk as well, and also on the IR boundary. And the Peccei-Quinn this Peccei-Quinn symmetry here is going to be preserved in the bulk and on the IR boundary, but on the UV boundary, I'm going to allow for maximal violation. And of course, because I'm in the warp geometry, I can easily explain the hierarchy of the scales, and that's not going to be a problem, and that's well known. Now, the axion is going to be sitting in some 5D scalar field, some complex scalar, and this 5D scalar field is going to have a bulk mass. So I'm going to give it a mass. It's got a kinetic term, but it's also going to have a mass. And I'm going to parameterize the bulk mass in units of the curvature, k squared, but I'm going to parameterize the mass in this way, delta times delta minus 4. It's a funny parameterization. Delta is just a dimensionless parameter, but I'm just going to parameterize it in that way. And we'll see, the reason why I do this is because this is going to map into the dictionary. There'll be a dictionary, and delta will actually have a meaning in the 4D theory. But for now, just think of delta as just some free dimensionless parameter, and the mass is in units of k. Now, when you solve for the scalar field in the ADS geometry, this is the solution. You can see that it depends on the z coordinate, the fifth coordinate, and then there are two terms. It's a second order equation, and there are two linearly independent solutions with coefficients lambda and sigma. Now, lambda, it turns out that lambda models the explicit breaking. So if you have a non-zero lambda, you're turning on explicit breaking in this solution. Whereas if you turn on a non-zero sigma, you have spontaneous breaking. And that's just the dictionary tells you how that works. And so the lambda and the sigma, because they're just constants, they'll be set by the boundary conditions. So you'll put boundary conditions on the bulk field, and you can turn on lambda and sigma and mimic spontaneous breaking of the Peccei-Quinn symmetry or the explicit breaking. And so now, so you can check, first of all, that you want to set up your problem that you just have a massless axion, right? You just have the symmetry is just spontaneously broken, and you have a Nambu-Goldstone boson, should have a massless axion. So first of all, we choose the boundary conditions such that lambda is 0, so no explicit breaking. And of course, you can solve the equations of motion. I didn't give you all those details because we don't need them. This is an approximate expression for the profile of the axion, and we're just interested in the lowest lying state of the Kaluza-Klein tower. The heavy states, we don't care. We're just interested in the axion. That's its approximate expression. And here it is. I've plotted the profile as a function of z. This is the UV end. That's where the UV brane sits. That's where the IR brane sits. And the profile is flat. And the profile is plotted for two values of this dimensionless parameter delta. So it's 5 and 10. And you can also check that you actually, in the low energy theory, you have the global U1 Peccei-Quinn symmetry is non-linearly realized as the shift. You see the shift, and that's why the axion is massless. So that's your starting point now. So you've put in all the correct boundary conditions. That's your starting point. And now what I'm going to do is turn on the maximal violation on the UV boundary to mimic gravity explicitly breaking the Peccei-Quinn symmetry. And so then you choose the boundary conditions. Well, first of all, you add a potential on the UV boundary that's going to explicitly break the Peccei-Quinn symmetry, and that's equivalent to having a non-zero lambda. And now you can again solve for the axion profile. And what you find now is the following. So here's the UV brane, here's the IR brane, and what you find as a function of delta is that the axion profile is exponentially suppressed on the UV boundary as a function of delta. So the bigger I make delta, the more exponentially suppressed it is. So this is good because you see what you're doing is you want the axion not to be sensitive to the explicit breaking on the UV boundary. So even though I've allowed for whatever you want to have on the UV boundary to break it, the axion is not seeing it, which is good because the axion should only see the explicit breaking from QCD and not from gravity. Now, because the axion is, the profile is suppressed, and because you've explicitly broken the symmetry, this non-zero lambda, it will generate a mass for the axion. And so you can work out the mass of the zero mode, the lowest lying state. And here it is. So this is the mass of the axion, from the UV explicit breaking as a function of delta. And you can see that as you make delta bigger and bigger, the axion mass just drops exponentially. So so this delta is controlling the suppression of the profile on the UV boundary. And the bigger you make delta, the more the profile is exponentially suppressed, the more the mass is smaller and smaller. And that's what you see here for just some range of values. So but what you see is that the UV axion mass is suppressed for large delta. You need this dimensionless parameter delta in the 5D Lagrangian has to be of order 10 to get a big suppression of the mass. So that's pretty simple. You can kind of understand it geometrically what's happening, but you also have to, the axion also has to couple to the gluons, and that you can set up by introducing a bulk Chern-Simons term, where the axion will then couple to the gluon. So this generates the axion-gluon coupling, and then the formula for the UV axion mass squared, it can be written in terms of the decay constant. And so there it is there. This factor out the front here is just some order 1 number, but the decay constant here, FA, you can see that FA is basically given by the infrared scale. And you can see the suppression here, which goes like, and the axion mass is proportional to FA. And I'm sorry, actually, I just realized I'm using capital FA now for the decay constant, not little fa. Sorry about that. But you can see that the axion mass is proportional to FA squared, but there's this suppression of the mass, which is proportional to delta minus 4. So when delta is 10, you get a big suppression here. If FA is 10 to the 9, lambda UV is m Planck, you get the big suppression, and so the axion mass is really small. And that's just, that's by construction. We put in the delta to achieve that feature. But why does this now solve the quality problem? Well, you go back to the axion potential, right? So here's the usual QCD contribution. So there it is. The minimum of this cosine is when this is 0, right? The axion vev cancels theta bar. And there's the QCD contribution out the front. But if I've got another source of explicit breaking, then I've got another cosine term. with my axion. But now there's also phases in the term coming from gravity. There's also complex phases there. They don't necessarily align with the phases in the standard model. If they did, you'd be done, right? So there's two ways to solve the equality problem. You can either align the phases from the gravity violation with the standard model, or you can make the prefactor here, you can exponentially suppress the prefactor and kill the cosine term so that this dominates and you preserve your minimum. And the minimum is you want the vev of the axion to cancel theta bar. And of course, I don't have any good ideas to align delta with theta bar. Maybe there are, but I don't know. So what we're doing is we just want to kill the amplitude of the cosine from this term that destabilizes the potential minimum. And that's what this is showing here. So we want this coefficient here to be smaller than 10 to the minus 10 of the QCD contribution. And then you can plot it. Let's just go to this plot. You can plot it as a function of the decay constant. You can ask yourself, what's the minimum value of delta that you need such that you still solve the strong CP problem? And you can see that for ranges of kappa, kappa was the coefficient in the Chern-Simons term. It was here. It's typically an order 1 number. But for various values of kappa, you can see that the minimum value that you need for this dimensionless parameter delta is 10. And that will solve the quality problem for this range of S.
Delta is a function of your original. But is delta a function of your original parameter? Is delta?
Delta was the mass. It was. Oh, this delta here. Oh, this is just some random. Oh, this was just the
complex parameter.
Yeah.
Is the phase of the complex parameter.
Yeah. Exactly. Yeah. And that can be anything. Yeah.
Is 0 CP, but now 0 is not a good thing.
But 0 is not a good thing because I'm allowing for CP violation on the UV boundary. So I can't take delta to be 0.
It needs to be theta bar.
But it needs to be theta bar, not 0. Yeah, yeah. So you have to have some random value there. So that's it. That's the model. And you can say, well, okay, you gave me this 5D model. You introduced this parameter delta. It's a dimensionless parameter, and it's got to be bigger than 10. It's like, okay, you've solved the problem, right? Well, if that was all that was it, I would also be uncomfortable. But here's the nice thing about it. It was no accident that delta needed to be bigger than 10, actually. So that's what I want to get the next point across. And that's because there's this holographic interpretation. So everything in 5D has to be understood as 4D strong dynamics. So if I have a solution here for the quality problem, then I've got to tell you, how does the 4D theory solve this in the 4D theory? Because there's a dictionary. And here I've given you the dictionary. I was trying to mimic a global Peccei-Quinn symmetry in 4D, which is actually a local symmetry in the bulk. I didn't give you those details, but that Peccei-Quinn in the bulk was actually a local gauge symmetry. I did tell you about the mass squared being delta minus 4, but now I can tell you why I chose that parameterization, because delta actually corresponds to an operator on the CFT side. It's actually the dimension of the operator. The exponential warping, that's like a dimensional transmutation. So that's why you get the infrared scale to be much smaller than the UV scale. The sigma is that you have a vacuum expectation value of this operator. That's the spontaneous breaking. And lambda is some explicit breaking. But now you can see why delta had to be 10, because it's actually the dimension of the operator that you needed to suppress in the quality problem. It was the little n being 10 on the first slide back here. Sorry, I don't like doing this because I normally lose track of where I am, but now I did it. You see, right at the beginning here, I told you that this n here had to be bigger than 10. But I've just engineered but on the dual side, that's precisely what's happened. These operators here are corresponding to some composite operators, and their dimension has to be bigger than 10. It's just a one-to-one mapping. That's what happened. Yeah, sorry. Oops, I think I've gone too far. So what's happened here is that this 5D axion with this local Peccei-Quinn symmetry in the bulk, it's actually dual on the 4D side to a composite axion, but the composite axion has an accidental global Peccei-Quinn symmetry. So it's just an accident that that operator only breaks Peccei-Quinn at dimension 10. Now, the 5D theory, it doesn't tell you what doesn't tell you the constituents of the 4D theory. The ADS-CFT correspondence never gives you that detail. It's just the chiral Lagrangian of pions. It gives you that description, but it never gives you the UV description. But when we wrote our paper, we came across this paper by Gherghetta and collaborators here, where they actually constructed a 4D composite axion model, which actually had an accidental Peccei-Quinn global symmetry. And it was just having an SU5 gauge dynamics. And all you do is you use gauge invariance and chirality, and you find that the first PQ breaking fermion condensate shows up at dimension 9. So, and that's just coming from gauge invariance. So this is equivalent to, in the standard model, we never worry about a baryon number or proton decay because it's an accident, right? At the renormalizable level, baryon number is preserved and it only comes in at dimension 6. Well, this is a 4D model where the Peccei-Quinn global symmetry is preserved up to a dimension 9 term. And that's what they had constructed purely from the bottom up in 4D. But this would be an example of, see, the fifth dimension is kind of capturing a whole class of accidental composite axion. Sorry, I don't know why I said Susie. Of accidental Peccei-Quinn symmetry with composite axions.
So 9 is not 10.
Exactly. So what happened in this paper is that they were borderline. And in fact, what you'd really want here, and that's coming from a 6 fermion term. These 5 bars and 10s, they're fermions. So the UV theory only has fermions. And because you have 6, but what was interesting is that gauge invariance forbid a dimension 4, a 4 fermion term, dimension 6, but the next term was 6 fermion, dimension 9. And you would, maybe there's another theory where you could have a dimension 12, which would be an 8 fermion term, but I don't know any example. But you're right, this was actually just slightly less than what you needed, actually. So that's it for the quality problem. As I said, it's dual to this accidental Peccei-Quinn symmetry. But now what you can do is you can say, okay, well, I've got this 5D framework. Can I then solve more problems? And the answer is yes. That's the beauty of the 5D framework, because now what you can do is you can then throw in fermions in the bulk and then also address the Yukawa couplings. And so solve the fermion mass hierarchy. It basically comes for free. Now, I'm not just presenting this because I know that it can solve the fermion hierarchy problem, mass hierarchy problem. I'm presenting it because when you do this, this solves the quality problem, it solves the fermion mass hierarchy problem, but then it gives you specific predictions for axion-fermion couplings, and it also gives you predictions for axion-fermion couplings which violate flavor. And the strongest bounds are on the flavor-violating axion couplings. So the model is predictive. You solve these problems, and then you get predictions out. So here's the basic setup. You can see that I've still got the basic setup with my Peccei-Quinn, but now I'm going to do a DFSZ model. So I've got 2 Higgs doublets in addition to the axion, and I've got the standard model fermions in the bulk. And then I'm just going to choose my profiles of fermions with the Higgses to solve the fermion mass hierarchy. And then once I've done that, it'll then fix the axion fermion couplings, because I don't have any more freedom in the fermion profiles once I fix them with the to explain the fermion mass hierarchy. So here are just some details of that. The Higgses, I'm just, for simplicity, we just took the Higgses in the bulk, H up, H down, to be constant, just for simplicity. There's the axion inside the complex scalar. And then you can write bulk Yukawa couplings between the Higgses and the bulk fermions. So this is an old story. And then the profiles of the fermions, they're controlled by these C parameters. So once you choose the C parameters, the fermion profiles will be fixed. So I don't need to dwell on this, but I just want to show you this picture here, right? So there's the left-handed fermions, there's the right-handed fermions. For simplicity, I'm putting the Higgses in the bulk, and the overlap will explain the fermion mass hierarchy. But again, notice that the background setup is my Peccei-Quinn model with solving the axion quality. And so these are plots that tell you where the C parameters have to be in order to solve the fermion mass hierarchy. And now, once you know that the C parameters are fixed, you then go and compute the axion-fermion couplings. The profiles are fixed. So you're doing an integral between, you're doing an overlap integral between two fermions and the axion profile. So in this model, the axion profile is fixed to solve the quality problem. The fermion profiles are fixed to solve the fermion mass hierarchy problem. So then you'll get a prediction for the axion-fermion couplings. So that's what I'm saying here. This is just the parameter count, counting how many C parameters you have in the quark sector, how many you have in the lepton sector. Then you fit to 6 quark masses, 2 CKM, 3 lepton masses, charged lepton masses, 2 PMNS, and there's 1 free parameter. And these are the predictions. So these are now the numerical results for predicting the flavor-violating couplings of the axion to fermions. So the way people normally parameterize this is that they define a 1 over FV for vector and axial vector. This is just some mass scale. And this is the axion decay constant, and the C here is just some suppression coming from the overlap. And now these parameters are chosen. So this parameter here, the infrared scale, is chosen to have a decay constant of around 10 to the 9. Delta is chosen to solve the quality problem. And then you scan over the 5D parameters. And you assume that the 5D parameters are all of order 1. So you don't put in any hierarchy. The hierarchy is coming out from the overlap. And then these are the predictions for the flavor-violating couplings, axion couplings. And you can see that there are bands here because you scan over the 5D Yukawa couplings, which are of order 1. So you have some range there, and you get these bands for the different flavor-violating couplings, up and down sector, and then these are the lepton flavor couplings. And you can see that the typical scale here is 10 to the 12 or even larger. And you have to compare this with a decay constant, axion decay constant, which is 10 to the 9. So now you can ask, what are the bounds on these flavor violating couplings? And it turns out that most of them are pretty weak, but there is one coupling which is coming from invisible decays of the kaon, which is this one. This is the SD, the vector-like coupling SD, and the bound is actually quite strong. It's 6.8 by 10 to the 11, and this is the future sensitivity for this particular coupling, and you can see the other ones are still much weaker. But this particular limit, this particular bound, will actually put constraints on our model, because we were predicting couplings around 10 to the 12. So you can use this experimental data, these experimental bounds, to put limits on this coupling FVSD. And
Sorry. Everything is fixed. So everything is fixed except the F. Except F.
Yeah.
Constant.
Yeah.
And the rest are fixed.
Pretty much, yeah.
Because you have flavor suppression are coming also, so some kind of Gherghetta suppression in this flavor thing. There's also Gherghetta suppressions.
Yeah. Oh, yeah. Yeah. That's why, you see, that's why this C here, you could actually write this C, these C's, in terms of Yukawa couplings, actually.
Now you have the suppression, but still is too large for.
But
Go back to still for K, I'm going to pi on A. This is too large.
yeah.
Then to the minus.
So here, this is
Inside the interesting win
yeah.
for this case.
Yeah. So this is now gonna put a bound on the model.
The bound is on F. You have to go F bigger than 10 to the 12 for tuning, some tuning.
Exactly. See, so here it's just a generic prediction for F. SD is this one, but this is for these parameters. But I can change these parameters just to be consistent with the bound, and I'll show you that now. It's here.
Not everything was fixed.
Well, it was fixed up to it was fixed up to order 1 parameters. It was fixed up to order 1 parameters.
Order 1, where? In what? In the exponent on the
No, in the prefactors.
to keep 3 orders of magnitude, 2 orders of magnitude to get into.
Yeah, but that's what I'm showing you here. I mean, but that's exactly what I'm showing you here, because these are predictions. You see, these curves here are predictions. I mean, it depends weakly. Remember I said that there was 1 C parameter that's left over in the quark sector. So that's what this is, but I keep this of order 1, and you see it doesn't vary that much. But each of these, so this is an example of one of the parameters that's in the model. It's an order 1 parameter. It was in my potential on the boundary. And you can see that here's the limit, which is 6.8, 10 to the 11, and here's the future sensitivity. So it's ruling out some region of parameter space, order 1, but there's still, you can still be consistent with it. Now here I'm keeping delta is fixed at 10, and I'm keeping the decay constant at 10 to the 9. Whereas over here, let me keep sigma to be 3 and vary delta now. And you can see that delta equals 10 if at this value of sigma is being explored by experiments. So the bottom line is that the experimental limits on this coefficient, the 1, 2, the SD, this lower limit puts limits on this model, which is roughly like this. But I do have freedom in the sense that if the decay constant here were 10 to the 12, then the predicted FV value would be even heavier. So obviously I've gone down to the lowest possible FA and constrained the model there, that one.
Because the previous one you have 3 orders of magnitude. If you want to go to 10 to the minus 9, here you have to be above 10 to the 12. No, the previous. Go back.
Back from here.
The experimental bound. No.
Oh, sorry.
Forward. But here tells no.
Oh, sorry, I went too far. Yeah.
Here tells you F has to be larger than 10 to the
12. It's 6.8, 10 to the 11, but let's say 10 to the 12. Yeah.
So if we want to go to the 10 to the 9, we have to go 3 orders of magnitude.
Yeah, but
Now, with order 1, I cannot get 3 orders of magnitude.
no. So this number here has to be 10, this has to be 10 to the 12, right? From experiment. It's this thing here. And the prediction for this number is roughly 10 to the 12 for a sigma naught is 3, delta is 10. But I just have to change sigma naught and I can change these curves. Yeah. Yeah, and that's what I'm showing you on this plot here. You see, I change the delta by a little bit, and you can see that the limit changes a little bit by order 1. So all the limits are around 10 to the 12, but there is some freedom in this sigma naught parameter. It's not changing by an order of magnitude here. I mean, because this parameter, it's just a prefactor. And you see that the prediction for FVSD is still 10 to the 12. But there's just a little bit of wiggle room. And then also you could play around with the delta. Now, of course, delta, we want it bigger than 10. But for sigma of 3, that's what it looks like. Okay, so that was the first half of my talk. And now I'm going to, for the last, because I have until 3, right? Is that?
You studied this 2.
Yeah, good. Yeah. So now, for the last 15 minutes, let me then tell you about how I'm going to change the axion mass and still solve the strong CP problem. So again, as a reminder that the axion mass comes from this 2-point function, which is referred to as the topological susceptibility. It's the 2-point function of GG tilde. Now, one way to, obviously QCD is strongly coupled, so you can't easily compute this, but one way to estimate the topological susceptibility is to use this, use the dilute instanton gas approximation. And here's an approximate expression for the topological susceptibility. But the important point is that it's exponentially dependent on the QCD coupling as a function of the size of the instanton. And you can see it here. Here's the QCD scale as a size of the instanton scale. And when the coupling is large, so in order to maximize the topological susceptibility, you want the exponent here to be as large as possible. And that means that the coupling has to be as large as possible, the QCD coupling. Well, that happens at lambda QCD. So at lambda QCD, the coupling is large, of order 4 pi. This thing is an order 1 number. That's the smallest suppression that you can have. And so that maximizes T. And then from this topological susceptibility, because QCD is asymptotically free, you're going to get most of the contribution from where the coupling is large, which is at lambda QCD. And in the literature, in the jargon is that you're getting the axion mass from large instantons. And what I mean, they're large size instantons, or the energy scale is infrared, but they're large in length. So that's the large instantons. So, but in addition, instantons mediate transitions between fermions, and there's a suppression between, there's also a fermion suppression that you've got to also put in. It's not just coming from this exponential, there's also fermion suppression. And at the end of the day, this is where you get the QCD prediction for the axion mass. But this story tells you how you could, in principle, change the axion mass. Because I argued that the axion mass is coming from large instantons where the QCD coupling is large. Now, the QCD coupling is asymptotically free, but we don't know what it is at 10 to the 11 GeV. What if the coupling were to rise again and become strongly coupled in the UV? You could get another contribution to the topological susceptibility from the large coupling in the UV. And so that's the idea. So how to enhance the axion coupling, axion mass is change the QCD coupling in the UV. Now, because you're going to high energy scales, you're going to smaller size instantons. So again, the jargon is that I'm getting a small instanton contribution. So again, you're speculating that the QCD coupling is of order 1 somewhere in the UV again. So it's not, so this theory would not be asymptotically free. So if you like asymptotic freedom, then this is not the theory for you, because I'm speculating that the coupling is becoming strong again. And then you can just go through and compute the contribution to the topological susceptibility, which feeds into the axion mass from these small instantons, and indeed you will get a new contribution coming from small instantons. And that way, that's how you would enhance the axion mass, but still solve the strong CP problem, because I'm only changing the coupling in the UV. I'm not altering the phases. I'm sorry, I'm not adding any new phases. Well, you might say, well, sometimes if you change the coupling, you might have to add new phases, but I want to change the QCD coupling without putting in any new phases.
Are you assuming this QCD coupling is asymptotically safe, or there's some sort of Landau pole in the UV?
Yeah, I'm assuming that it's going to be, obviously I'm going to assume that there's some strong coupling, and then some theory, some other strongly coupled will take over, some other description will take over. So the simplest way to do this without introducing any new phases is to use a fifth dimension, because if you use a fifth dimension, we know that the coupling grows in the UV, and so you could use small instantons in the fifth dimension to make the axion heavy, and there's no new phases around. So that was our idea. And now again, we just have a very simple model that can realize this. Here's our setup. So now this is just flat space. So we just took a very simple model here. So it's no connection to what I said before. There's no quality problem here or anything. Just a simple trying to bump up the axion mass. So this is the gluon in the bulk. So the gluon, because you've got gluons in the bulk, it'll make this QCD coupling very large. And the U1 here is just to provide for you the axion field. So what you then have to do is you have to take the instanton solution in 4D and uplift it to 5D. And when you do that, it'll solve the 5D Yang-Mills equations, provided that the fifth component is 0. And then what's critical in all these computations is that you need a solution which has finite action. Because if you have infinite action, then you're not going to get any effect. So here there's a finite action because you're imagining that the fifth dimension is compact. And so there it is. And so now here's the cartoon for what's going to happen. So here's the cartoon. So this is so here's lambda QCD as a function of the energy scale. So as I go up in energy, at some point, I'm going to see the fifth dimension, and now the coupling is going to grow. And when the coupling grows, the QCD coupling will give you a new contribution to the topological susceptibility. And so here again is here's the approximate expression for the topological susceptibility. There's the action. And what's interesting in this model is that the action picks up a power law term. So here's the usual 4D contribution, which is this part here. But there's a power law term, and this power law term, it actually cancels the 4D contribution, and in other words, it minimizes the action so that you get a large contribution to the axion mass. And here's another way of stating it here. This is some approximate, for these approximate values, you can see that this power law contribution can overcome the suppression. You see, because see, this is the suppression coming from QCD being asymptotically free. So the coupling here is becoming weaker and weaker. So this ratio is really large, but now you're turning on this power law, which cancels that large contribution. And so the overall sum is still small. And if the exponent is small, then the exponential suppression is not that large. Okay. I don't need to go through this, but so now you just turn the crank and compute the axion mass by turning on these small instantons. Here are just a couple of details, but let me just give you the, well, you have to worry about perturbativity. So we want to trust our calculation. And so we want to make sure that we define this epsilon parameter, which makes sure that the coupling, that we can still trust our calculation. So we need this epsilon parameter to be less than 1. And here's a check that you do get a positive exponent, a positive action, that there's enough room here that you can play around. Provided epsilon's bigger than 0.14, there's enough room to get an enhancement. And so here's the figure. Oh, that's not. So here's the axion mass compared to the QCD prediction. And so if this ratio is bigger than 1, you'll get an enhancement of the axion mass. And now this is a function of the extra dimension scale, 1 over r. And this is where the QCD coupling would start changing. So here we put 10 TeV, and we went all the way up to 10 to the 10 TeV. And what you see here is you can see that, you know, if you put an extra dimension at 10 to the 8 GeV, you can get enhancements of up to 10 to the 8, 10 to the 10, etc. This is an enhancement above the QCD prediction. There's also an upper limit here. This is some work that I was doing with my student and Maxime Pospolov, where we imagine that there's other sources of CP violation in the UV, and that can also that kind of puts an upper limit on how far you can enhance the axion mass. But at the end of the day, what the conclusion is that the small 5D instantons can dominate above, if you put an extra dimension above 100 TeV. And here are the, so now you can say, all right, here's the heavy axion. So what are the heavy axion limits? So again, I'm plotting the coupling 1 over FA as a function of MA. Now this plot's a bit busy, but here's the QCD Axion line. And with this 5D model, you can move off the QCD Axion line and solve the strong CP problem. Now I've taken this plot, and my student is he's gonna update this plot eventually, but I took this plot from the Agrawal-Howell paper. This is an alternative way to get a heavy axion. And they had they were using sites, a moose model to do it. And you can see that they have their benchmark models for increasing the axion mass off the QCD line. So that's what these benchmark 2, benchmark 1 means. But the solid line there means that if you were to enhance the axion mass to this range, it could still be the dark matter. But once you get into the dotted part, the axion now is so heavy that it decays before the lifetime of the universe. And the limit is around 20 eV. If the axion mass is heavier than 20 eV, then it can't be a dark matter candidate. And you can see here that the dashed lines would be regions where you've enhanced the axion mass, but it can't be the dark matter anymore because it's just too heavy and it decays to photons. So what we did is that we used the heavy QCD axion not to solve the dark matter problem. We used it to provide the axion now is not a dark matter candidate. It actually solves the baryon asymmetry. And that's the window that we use. But we use this axiogenesis, which is a Affleck-Dine type mechanism generate the baryon symmetry, but you need a heavy axion around 1 MeV to 10 GeV. See, you see how you're off the QCD line and you're up in this window. And so in other words, you can still solve two problems. You can still solve strong CP, but now you solve the baryon asymmetry, but not the dark matter. Of course, this just shows you that I didn't mean to imply that we were the first to have this idea. The idea of enhancing the axion mass, it goes back to the 80s, Holden, Peskin, Flynn, Randall, and then there was there's been further development over the years, and more recently a lot of work has been done. So I just put a bunch of references here for people if they want to also look at these other papers. But I also use this to make the point that, you see, if we were to find an axion mass that's off the QCD line, you will immediately then speculate that there must be a UV completion, which changes the coupling of QCD to enhance the mass of the axion, you see, because now you've kind of opened up all the parameter space on the heavy side, and you can still solve the strong CP problem. So I find that interesting. Whether it's plausible, whether you plausibly believe is another question, but at least now you can argue that I can still solve the strong CP problem off the QCD line. So here are just some, yeah, I'm done. So here are just some questions that we're still thinking about. This is related to Alex's question. Yeah, it would be interesting to construct a model where you would actually see the suppression. That would be like an 8 fermion term. That would be nice. Doesn't exist right now. Obviously, you could do some more 5D model building. You could apply this to any ALP. And of course, yeah, you could ask, and Alex and I, we asked this question: what happens if you do put it in a warp dimension? Could you enhance the axion mass? And the answer is that no, because it turns out that the only solution with instanton number 1 has a very large action. So the action is basically really large. And so remember that the action appears in the exponent. So if the action is large, you have e to the minus action. The action is large, you'll get a very small contribution to the axion mass. So it turns out that in the warp dimension, it doesn't look like you can enhance the axion mass, which is interesting. But we had some arguments for why that's plausible. And we also found other solutions in the bulk, which are non-trivial solutions of the instanton. But maybe there are other ways to enhance the axion mass. All right, so this is just my summary. You can solve it. Axion quality can be solved in 5D, and that's the dual interpretation. Then you can flavor this solution. You can flavor it. In other words, you can end up putting more constraints on the model by solving the fermion mass hierarchy. The feature of that is you predict these flavor-violating axion-fermion couplings. I didn't have a chance to talk about the light sterile neutrinos. You can go into the neutrino sector. You can predict light sterile neutrinos. And then finally, you can use the fifth dimension, the small instantons in the fifth dimension to enhance the axion mass. And therefore, the axion mass then is it's a sensitive probe of UV physics. Thank you.
Thank you very much for the nice talk. Other questions or comments?
In terms of the point here where you say it solves or it explains the fermion mass hierarchy problem, I don't really understand the extra dimension stuff, but it seems to me that you're using them as input parameters.
Yes.
So how does that really explain that? Isn't that just moving the problem from?
Oh, what I'm doing is I'm adding order 1 parameters.
Right.
But I'm getting a hierarchical Yukawa spectrum. So that's what's coming out.
But are these order 1 parameters somehow tuned in such a way that?
No, they're just order 1. Yeah,
Oh, okay.
That's right. Yeah. So, yeah, I mean, it's like when people solve with Peccei-Quinn Froggatt-Nielsen, not Peccei-Quinn,
yeah.
right? They put in order 1 charges. Well, sometimes they're order 10, but you put in order 10 charges and you get the hierarchy. Here you put in order 1 C parameters, which are bulk fermion masses actually, and then you get the hierarchy for free because the predictions depend exponentially on the C's. So that's where it's coming out. And sorry, I did go quickly through that because
Yeah, okay.
yeah, I just because of the time.
Yeah, that's fine.
For biogenesis, what is the requirement? My body is needed.
Yeah, what you need there is this work of that's this work here. I didn't really do it justice by putting this little thing here, but what you're for the baryogenesis to work is you need some angular momentum. So the axion, see, the misalignment mechanism assumes that the axion starts rolling from rest. And that's been the assumption. And then recently, these guys, Raymond Coe, Harry Gaia, and also earlier work by Lawrence Hall and these authors, they suggested that if the axion were actually moving, there would be an angular momentum, and that angular momentum ends up turning into a baryon asymmetry. It's related to this Aflac-Dine mechanism that's from the 80s. But that's what I'm using here. So the axion does not start from rest. See, when the axion is displaced from its minimum, it's not starting from rest. It already has some angular momentum. That's kind of what I was trying to show here. But that angular momentum is some U1 charge, and that ends up being processed into a baryon number via Sphaleron processes. So, sorry, that's...
Is it realized or user case with?
Sorry, I couldn't hear.
Is it realized or user case with?
Oh, with the KSVZ model, you said. No, I mean this just assumes that the axion just has some initial speed. That's it, and has some angular momentum. So this is the wine bottle potential, and you can see that it's kind of rolling around. So that's the assumption. Yeah, and I think it applies for any KSVZ, or I think it can do both. Yeah.
You put the Chern-Simon at the beginning, and the second model you put the Chern-Simon.
Oh yeah, I did. I just didn't say it. You mean the 5D, the flat one?
No, the first model.
Oh yeah, they all had Chern-Simons. Yeah, they all had them.
So you get it from the mixing of the Axion to the Higgs, no? Or the coupling to the.
Oh, you mean? Oh yeah. I mean, the axion is a linear combination of the Higgses.
The two models, why don't you integrate heavy quarks? Okay, and you get the coupling of the axion to
Fermion.
Dual from Fermion integration. The other you couple to Higgs.
Right. Yeah. Sorry. The other one is coupling to Higgses. Yeah.
So the second model you didn't put Chern-Simon.
Right. It's a DFSZ model. Yeah. Yeah. Sorry. Yeah.
The first one you put Chern-Simon. So Chern-Simon is anomaly.
Yeah. It puts the anomaly on the boundaries.
Now what you do?
And now what happens is that because what happens is it actually breaks the local gauge invariance. So when it puts the anomaly on the boundary, you're forced to add another term to cancel it on the boundary. So you add an axion-gluon coupling on the IR boundary to cancel the part coming from the bulk, from the Chern-Simons.
So you put a contact term in the.
On the IR boundary, yeah.
The action is in the phi, the guy in the guy.
The axion is actually it's partly in the V phi, it's partly in the gauge boson and partly in the phi actually.
How about you do a combination?
Yeah, it's a combination.
How you write the terms?
Yeah, yeah. You just end up getting an axion GG tool. You just put on the boundary, and that ends up cancelling the local gauge anomaly in the bulk.
The term is before you decide to break the symmetry. The term should be before. I mean, you turn on the profile, you break the symmetry, but you could say you don't put it. Normally it should be cancelled. So it should be a way of rewriting without gaps from the original fields.
From the original fields?
So you have to put a log of phi there.
You mean from the fermions integrating out? There would have been fermions on that boundary that I integrated out. That's what would have happened, you see. Because if I put this dimension 5 on the boundary, there would have been fermions there that I integrated out that would have given me this term.
I'm saying, instead of the action, I have to write it as the original field phi. But then
Yeah, there would have been, I think there would have been a log phi then, probably, I think.
Could you show the slide about heavier action?
Oh.
I mean, you listed a lot of other approaches.
Oh, yeah.
So, all of them are within 4 dimensions.
Oh, yeah, sorry. These are all
These are
4
all 4 dimensions. And
Yeah.
I mean, in your mind, so in these models, and also in your case, you have a flat 5D extra dimension, and that can have a heavy action. In your case, do you affect other part of the QCD or not? Like UA1 problem or
We don't think so, yeah, because,
the data?
yeah. Like, for instance, the eta prime mass, it's going to be, because it comes from a 4-quark operator, it's going to be suppressed by the small instanton scale, and that'll be in the denominator, but in the numerator, it'll be lambda QCD. So it'll be the effect on eta prime, the mass of the eta prime would be lambda QCD over the small instanton scale. So we believe that, yeah, there's no effects.
Touch.
Yeah, because everything's going to be sensitive to lambda where the strong coupling is in the UV. That will always appear in the denominator.
And for the ADS5, you have a 4-dimensional interpretation in terms of the strongly interacting gauge theory.
Yes.
So you have something analogous for flat extra dimension case? No, okay.
This is why we wanted to look at the axion mass enhancement in the warp dimension, because then we thought, then we would get a dual interpretation. But we went looking for trouble because we found that the action is just way too big, because the solutions, the instanton solution, it doesn't naturally uplift into the warp dimension now. See, in 5D, it's quite nice actually. This solution, yeah. This has instanton number 1. That's the usual 4D solution. Just depends on X. That's the size, the center. That's the 't Hooft symbol. But you can take this solution and uplift it to 5D, provided you turn off A5, because the A mu has to go into a 5D gauge field. And so this thing will still satisfy the 5D flat Yang-Mills equations. But when you take this solution and uplift it to warp space, the Yang-Mills equations are modified, and this doesn't work anymore. With instanton number 1, right? Because we want to identify the instanton in the bulk. But But what can happen though is that this thing can actually be, sorry, actually I'm kind of confusing things here. This thing can uplift, but if it uplifts, it doesn't depend on the z coordinate. Sorry, I said that wrong. You can uplift this in the warp dimension, but it won't depend on the z coordinate. But because it doesn't depend on the z coordinate, this solution will just extend into the 5D. And then when you integrate over this solution, you get a big action. So what we were looking for is to take this solution, but have it just be localized in the fifth dimension, in the ADS space. Because then when you integrate over z, you get a small action, big enhancement for the axion mass. So sorry, you can uplift this to warp space, but that's not the solution we wanted. We wanted the one where it would be localized and give us a smaller action. And instead, we did find localized solutions, but they had instanton numbers 0. So it was instanton, anti-instanton, which doesn't help you for the axion mass.
Can we thank the speaker again? Thank you.